JWST, the James Webb Space Telescope. And there it is, beautifully deployed. This is an artist rendering of JWST. It is an infrared observatory, hence those big shades that were designed to block the sunlight from it and keep it cool, have all the heat radiate away from the big mirrors that were up top, and the electronics and everything down below that creates heat could be kept away from it via these big sun shields. So incredibly complex satellite, really, or spacecraft that we were sending out. It did launch. It was launched on a European Ariane from French Guiana on December 25th, 2021. So it was launched at the very end of last year, a little more than a year ago, but it was on Christmas Day. So those that celebrate thought of this as a great gift for all space flight fans and all fans of astronomy, thinking there goes our telescope. Here is that sun shield deployed in a lab, of course, so you can see how it compares to a person. It's about the size of a tennis court, and there are 5 layers. Craziness. It's really amazing how this stuff worked. The mirror itself is enormous. You can see how it compares to a person and how it compared to the Hubble Space Telescope mirror. Now, this was 18 individual segments. Now, how do you have 18 segments all make a single image? Well, what you have to do is align all of those mirrors. You have to tip and tilt them until they all point to the same position and bring all those dots together. And you can see sort of an actual little movie of that happening. Those stars are coming into a focus and each becoming a single dot on each of the mirrors. And then, of course, these same tools can be used to sort of take an image of the mirror itself. And this is the alignment selfie. So we could say, yep, there they all are. And we are seeing light in all of them. Sort of the first light image that we got to see, the alignment evaluation image. Everybody was still very excited about that because, boom, diffraction spikes, those big spikes that are coming off the star in the middle, the 6 big ones, and then the sort of smaller horizontal one. Those are due to the optics of the instrument, the telescope and the instrumentation. So it was a good sign to see those and to see them look so sharp. It was really incredible. Now here's a comparison of an old space telescope, Spitzer, that was retired. There's the Spitzer image, and here's the comparison of the James Webb, JWST rather. Catch myself saying the whole name. And here's the image of JWST's image, how much sharper that is. It's like putting your glasses on. It's really quite amazing. Now you can see a couple of the measurement for the ground segments on the left-hand side, or ground measurement on the segments, and then a recent best mirror alignment. Well, you can see that one in the lower right that has that spot. What's going on there? Well, it turns out there was an impact. A micrometeorite came in, impacted that mirror, and actually damaged it. So this is something we knew could happen. We were a little worried. I think everyone was somewhat surprised it happened this early on. So they are going to take some actions to try and prevent this, and namely that's pointed away from where these things come from. Only observe in the other direction. And it does turn out that there's a preferred direction to have these micrometeorites come from. They can come from anywhere, but in general, they're going to come in the direction that the Earth is moving in its orbit, because the Webb telescope travels along with the Earth in the orbit around the sun. So you want to point away from the direction you're heading. It's kind of like it'll observe out the back window, the back window of the cars we're driving, rather than looking out the front. Now, here's one of the beautiful images it took, of course, one of my favorites. This incredible structure we're seeing in the nebula, the Carina Nebula, of course, the cosmic cliffs as they call it. And we're peering deeper into it, seeing pockets of star formation that we'd never seen before. Of course, it released these other beautiful images as well. Here's the Stephan's Quartet, which, believe it or not, only 3 of those galaxies, or the 3 up top, are actually at the same distance. The one that's on the left-hand side is not at the same distance. It's in the foreground, and you can see that in the imaging. It breaks into individual stars, whereas the others do not. Took some images of dying stars. These are what are called planetary nebula, and this is the Southern Ring Nebula, and it's just a gorgeous image of the death throes of a star, where it's throwing off its outer layers, and those layers are glowing from the heat from the inner star that's dying on the inside. You're seeing these deeper layers that are still very hot, and that outer glow from that gas. The Webb also has a spectrograph on it, and you're able to measure things like this atmosphere of an exoplanet, a planet going around another star. We were actually able to see in some of the very first imaging the composition of an atmosphere, and it'll just keep getting better. And in that first imaging release, of course, they released this beautiful image of the cluster, and everybody was, of course, just loving the galaxies that are in this. You can look at the little tiniest thing in here, and it's probably a galaxy. Um, some of these are some of the earliest objects that were forming, but meanwhile, that cluster in the foreground has that big smear and swath of light. Let me take the laser pointer here and show you what I'm talking about. You can see here this loop that comes up over and goes around. Well, it was kind of confirmed that that indeed is probably intracluster stars, stars that have been ripped out of their galaxy in the foreground cluster, sort of creating this background glow, or foreground glow as the case is in this image, because most of the galaxies are in the background. Speaking of background galaxies, they were measuring Z's, which is, it's a measurement of distance, really. It's how many times the light has been redshifted. It's the redshift of the galaxy. And the bigger the number, the further away it is. And needless to say, a Z of 20 is something like 13.5 billion years ago is when the light would have had to have left it. And people were claiming those sorts of redshifts off these objects. I do think that we need, I need to go into the literature and find what are the actual spectroscopic measurements. We're going to need to start taking some spectra of these if we can, if they're bright enough, and find out, really nail it down, because most of these estimates were based upon colors of the objects, which colors can change depending on dust and stellar composition and other things. They're pretty good, but we can do better with spectroscopy. Speaking of spectroscopy, JWST is outfitted with an instrument that can do spectroscopy. That's the NIRSpec instrument, and others. MIRI's in there as well, and it can do what's using called an integral field unit, where you can get a little spectrum of each and every pixel, or at least ones that you've chosen in a range. Needless to say, look on the very bottom, crossing it. I'll get my laser pointer out here again. BVRI, well, B stands for blue. That would be the blue color I see. V is sort of a green band, visual or green. R is red, and of course yellow and orange are in between. So the JWST, it can't see green or blue at all. It's not very good at seeing yellow or orange or plain old red. And most of the images, most of the instruments have the vast amount of their sensitivity in what's known as the infrared, or the wavelengths that are slightly longer than plain old visible light, just so you can see what sort of instruments available. There were some problems with the MIRI instrument, but it turns out that it's back up and running and working just fine again. They found a workaround to make it work better. I want to end here just with a couple of beautiful pictures of the Tarantula Nebula, which is actually a star-forming region in our neighboring dwarf galaxy that orbits our own, the Large Magellanic Cloud. So the Magellanic Cloud is a dwarf galaxy that goes around our Milky Way, and it has its own stars that are being formed in it. And this is a dense region here that are forming stars. And JWST was able to make these spectacular images. And this is the MIRI instrument taking an image of that same region. I'm not ending here quite yet. Of course, I've got Neptune to talk about, and that beautiful image with the ring that we talked about before. And you can see here that that's Triton and other moons with Neptune there glowing ghostily. There were other images of galaxies at other distances, other galaxies fields have been taken. And finally, a couple to round it up here, I keep wanting to end the section. I feel like I've been talking a long time. The Spitzer telescope, again, that previous infrared telescope's on the left-hand side, and JWST with NIRCam is on the right-hand side. Now you might look and say, well, what's that sort of fuzzy stuff that's in there? Well, if you zoomed in on this image, you'd notice that those are individual stars, and we're actually looking through a dwarf galaxy. And JWST is able to break this dwarf galaxy into single stars, which is pretty darn cool. It can see baby stars being formed. This is actually a star forming region, and this is a single star with a dark disk going across it, and material flowing off the poles of this new stellar system that's being formed. JWST is able to measure chemical compositions in atmospheres. And you can see here one of the papers where they did that. These wiggling lines in the right-hand part over there really are what is a spectrum, and you can go and fit it. And the amazing thing here is that they were able to see SO2, which is sulfur dioxide. They didn't expect to see that, but they went in and did find it. And sulfur is an important element for life. So this planet probably doesn't have life, but it's interesting being able to start to piece apart these atmospheres of planets going around other stars. This is, I mean, this is, okay, not quite Star Trek level stuff, but as a kid, if you were telling me we were measuring the composition of atmospheres from a spacecraft we had deployed, I mean, this is awesome, awesome stuff that the Webb is able to do, JWST. Anyway, I'm going to move along. Just very recently, the NIRCam instrument was used to image Titan. Titan is a moon of Saturn that has a nitrogen atmosphere. Now, Titan is one of my favorite moons. I've always thought, how cool is that? The atmosphere is almost all nitrogen. That's what Earth's atmosphere is. It's almost all nitrogen. We got some oxygen in there too, which we need. Ever-growing CO2, which isn't so good. But Titan, all that nitrogen, well, maybe we could just add some oxygen and we could go live there. Well, problem is it's freezing cold. It is so cold there, methane and ethane turn into a liquid. So they're not even gases. They liquefy, and it rains methane, ethane. There are seas of it. It has a whole hydrological cycle, and JWST can see clouds in the atmosphere and surface features of this moon of Saturn from its location using its infrared instruments, which are just incredible. You can see there cloud A and cloud B that they feel are up, again, up in the atmosphere, and then that we're seeing down to the surface. And we're able to see sort of surface colorizations down there. So I never thought this new telescope would be able to see features on a moon of Saturn this clearly and be able to sort of follow clouds going around it. So just amazing stuff.